thank you to everyone for being here. Let me just very briefly introduce my company, PM10, born as a spin-off from the Genoa University, in particular the Environmental Physics Lab of the Genoa University. Our services mainly belongs to the atmospheric side of any kind of study you can perform in atmosphere. So from the experimental point of view, monitoring of the air quality and anything else, but also from the simulation side, so the evaluation of the impact of several pollution sources in the atmosphere. Our portfolio is quite wide. We work with both research institute and private, small to big companies. But also we have a quite great history in the field of funded project, devoted also to the evaluation of the impact of the pollution sources on the air in the urban area related to port activities. I've shown in this slide just a few examples of projects which are ongoing now and all related to, in some sense, the same final target, that is, understand how things are going on and develop innovative tools to intervene, to promptly intervene to mitigate any kind of issue. But let's go in details to the prompt project and our role in the project. Well, I will repeat in some sense what my colleagues said before about how prompt the SS strategy is. So you, from the side of, let's say, simulation, you start from a big waves and meteor databases, which is part of the skills of the Genoa University. From that database, you identify several scenarios. Mattia shows how these things happen. Then after, when something happens, you can just order this kind of scenario from the most likely to happen to the less likely, of course, with the percent of probability that things are going in that way. So you can use that scenario. That scenario is used to feed simulations of both water dispersion and air dispersion, so dispersion in the atmosphere. And our role was mainly related to the atmospheric side, so the meteorological simulation and the atmospheric simulation. But to anyone, maybe not all of you is in this field, so let me briefly give you an idea of how things are going back end. Any kind you have to deal with an atmospheric dispersion simulation, you start from the core of the simulation, which is the dispersion model, in this case high split, which is a Lagrangian model developed by NOAA. And you have to feed this model with three different kind of inputs. From one side, the meteorological input, that means basically winds to force the transport, and any kind of meteorological parameter is relevant to define the dispersion in the atmosphere. A kind of static input, that means you have to decide where the simulation must be performed and describe the domain. And last but not least, also because it's one of the most critical points usually, the emission input. So when you have something which tells you where things are going on, you have to tell to this guy which things is going to be dispersed. And from the first beginning, we worked on the meteorological side, so we developed the chain, which were used in three different ways. From one side, the outputs of the simulation were directly used in the prompt platform. And the same kind of simulation, meteorological parameters were used to feed the transport, the dispersion chain, but also, and this is one of the most interesting thing in prompt, I guess, is that those kind of meteorological data were used also to calculate the emission. That was the work performed by IH Cantabria, described by Anna in the last presentation. But when you want to perform this kind of work, you have to deal with some issue. First of all, you want to use well, relevant and detailed meteorological parameters. When you work with the meteorological fields, at the very beginning you have global models, but those global models are absolutely okay if you look from to a global scale, so the whole world, or maybe a big continent or something like that. But if we move to something which is like a port side, a port city like Genoa, you can immediately see that this can be not enough, because you don't have resolution enough. You do not have the final information you really need. You can see that looking to the outputs of the simulation. On this side of the slide, you see which could be a comparison between the forecast, the like original forecast, I would say, the global scale modeling, and the observation, the blue dots. Well, in this field, you see immediately that something is missing. Maybe the trend is okay, but you are missing a lot of events. So things doesn't work in that way. On the right side of the slide, you can see immediately comparing two different simulations. The upper one is 10 kilometer spatial resolution, and the lowest one is 10 times higher, roughly 10 times higher resolution, 1.1 kilometer spatial resolution. Well, in this case, there is something that you're totally missing. So these kind of features are totally different from that picture. So what we did is just, okay, let's just downscale. Let's start from the lower resolution and go to high resolution, and implement some statistical and AI models to take account of possible features, so go in details and calibrate in some sense the model. And that is the result with respect to the same picture we showed before. So well, it works at the final end. You have your target. So moving to the emission point estimation, well, I will give you here an overview of the results of IH Cantabria work well, towards our target. Well, you can see, looking to Aqaba and Tripoli, well, you have several different points. Anna showed you how things were going. But in each case, you can consider different meteor condition. And this is absolutely relevant. So it's very highly impressive, this, because in such case, of course, you have different belonging of the dispersion. So in cases like that, you have very high emission at the very beginning, but things are lowering very quickly. So things are completely changing. It's not only a matter of sources that are moving to the harbor. That was another aspect crucial, but it's also a matter of well, the weathering phenomenon. So how things are going in time. And this obviously completely changed the sketch at the final end. just collect here some few example of, more than thousands of simulations were performed to catch all of these different scenarios from both meteor and emission side. And what you can see looking at those videos is that different meteor conditions, I just took here wind rose, generates, we are considering the same event, so the same place and the same kind of release, but different meteorological conditions. And the pattern already seems to be totally different. Even if you are dealing with the same event, the different scenario have a totally different impact. That was something which immediately goes into the hazard and risk assessment. Also because we are working with coastal areas, inhabited or not. Well, it's totally different if any kind of toxic cloud goes to inhabited places or to the open sea, of course. Well, finally, what we have, I heard a solution modeling chain based on this 40 years database analysis, and this emission coupled with meteorological data. So we have more reliable and accurate atmospheric pollutant dispersion simulations, and the ability to quickly respond to any kind of accident, because things have already been done and are ready to, also in that sense, it's most easier and it's faster to have this kind of, thank you for your attention.